Okay, testing. Okay, so hi everyone. Let's get the reinforcement learning practical started. So yesterday we learned about the intuition behind reinforcement learning, and we also play around with the grid world. Basically, it is parameterized by a bunch of grids. And today we will be looking into the deep Q learning, which is a neural network approach to reinforcement learning. So in the grid world yesterday, what we did was we construct an environment that is an array, like 2D array. Then we can program our agent to move around in that array, and we store the utility function inside another separate array, which is even bigger, right? With height and then action. So that is like a 3D array. But what happens when the complexity start to increase? So now we will be looking into the deep reinforcement learning, where we parameterize our Q function as a neural network instead of just a table or an array. So you can follow the QR code and get the notebook as well, right? So when you have the notebook, I think I will try to run it in the meantime as we go through, because at the very end, then there is also some visualization and demonstration. Yeah, so this is the idea. So this is the similar to yesterday. We will have oh crap. Yeah, never mind. It will be running. Why is it not? Import T4, yes. Running. Okay, yes, it will be running. And so now the code is more, it also prints out the duration. So what is it doing? This is card poll. Card poll. Yes, card poll V1. So if we search gymnasium card poll. Yeah, so many of the standard. So yeah, so this is the what are the state, right? So the state is you have the theta and then the angular velocity. You also have the distance and the velocity of that as well. So here the state is 4, which is more than yesterday. Yesterday the state is 2, x and y. The grid is 45 cell, but the state that the agent observed at any point in time is only 2, x and y axis. Here it is 4. So theta dot, x and x dot. And then the action is still quite simple as well, 0 and 1. But it is to highlight the fact that as we increase either the state or the action dimension, we will have a different, it will become more complex, and we might need to use reinforcement learning. So this is how it will work. And I didn't have any visualization in the code. There will be a visualization at the very end, because while we're training, we don't really want it to show the rendering because it will take a lot of time. So the idea here is that, yes, it will try and see. So what is the reward? The reward is the duration. As long as it stays straight up, then the duration will increase and it will get more reward. So unlike yesterday, the more the agent is inside the environment, the more we punish it, because we want it to go quickly towards the goal. But for this one, as if it continues to stay up straight and it doesn't terminate, then it will gain reward. So that is a slightly different way of defining reward. And then down here will be a final like testing and visualization, right? So similar to machine learning, after you train, then you take it out to get the inference. So now let's get to the back to the code. So now let's revise. I also want to take this time to also like revise the idea yesterday, the idea of the utility, and like propagate the utility like into the different states. So first, let's start with a simple example. Yeah. So first, I would like to introduce this idea. This is just simple linear interpolation, okay? Simple linear interpolation. So you have a starting point of x1 and the starting and x2. So this x1 and x2, they can be an array. They can be a number, they can be an array, they can be a vector, basically a vector. The point is that we can draw a line between x1 and x2. Yeah, draw a straight line, linear interpolation. And then we would say that we can say that, okay, if I want to go a percentage away from x1, like between if x1 is 0, x2 is 1, and I want to go a certain percentage in the middle, then where would I land, right? What is the value there? So we have that value will be x3, and then how do we calculate that? We calculate that by using this equation x3 equals, x1 plus x2 minus x1 times tau, right? This is quite, you can visualize that. So I don't really annotate here. Yep. So let's say if this is annotate. Right. So if this is our origin, right? Depends on what you want. Like, is it a 2D or 1D? I don't really care like where the origin is. But the idea is that we can, if we want to define x3, we can use this formulation to calculate. Right. So the simple idea in this single line is that you have your starting point and then you have your end point. Then you take the difference between the starting point to get the linear, the middle line connecting them. And you want it to offset how percentage away from x1. So that is how you can understand this x3 as two components. Like you starting from x1 and then you do how percentage away from x1 towards x2. And then this is just another way of looking at it, like just shuffling around. So this is just grouping x2 and x1 as two separate terms. Yeah, so x1, x2, and x1, you can call that the error, the difference, or the linear interpolation, right? The linear difference between x1 and x2. So why do I bring up this? Because it is the idea, because it is a very simple step to saying that, yeah, so if we are starting at number 1, we want to move towards number 2 by a certain percentage. Where will we land? We will land in x3. So how is this relevant? It is relevant because, yeah, so how do we move and update towards a desirable value that we want? And that will be the case that it will be like this, right? So the equation, the Bellman equation yesterday that we encounter, this understanding first. Yeah, so if we have a current place, the current position that we're in at x1, we want to update towards a desired value, but there is a certain learning rate, right? A certain percentage, then we would land in x3. And this is like the math, like x3 equals this, but in programming we can us equals us is like override, right? So it overrides. So basically the idea is we want to update the value us by this alpha, which is the learning rate, times the error. And what is this error? The error is from our current state and from our current state to the desired value that we want, from our current value towards the desired value. So it will generally have this form. And I introduce this because, yeah, it is all, learning is all about pattern recognition, right? When you see this pattern, you know that, okay, it is updating. And this is also generally in machine learning, how they write it as well. So the new weight will be equal to the old weight plus a learning term times the error, the correction. Yeah, so pattern recognition. If you see this, you can understand what is underneath. So how does that work? So now we would replace the u desired with our Bellman equation, right? So yesterday, like we said, we can technically construct the utility values for all of the states, and that utility values will signal the desirability towards a goal that we want to achieve. So in the best case scenario, when we have all of the knowledge of the utility, right? If we have all of the knowledge, this equation will hold, right? If we have all the knowledge, this equation that relates the previous. So this is the current state. U prime is the next state that we want to go. So if we have all the knowledge of the utility, this equation will hold by this by this connection. There's a reward and there is the expected utility of the next state, right? So this will be our desire. Then we sub that in, right? When we sub that in to our desire. So yesterday you can see that there are like two different ways of calculating. Like there's a SASA and then there's a Q-learning. And then if you go back and look at the code, then you can see that, yeah, you can start matching one by one. So the first term is just U. The second term is the same, but it's just that now we are like updating it. There's an alpha, there's a reward, there's a gamma, and you can see the difference is somewhere here. So the SASA is taking the value from the Q table, whereas the Q-learning is taking the maximum action. So that that signifies the two different approach. If you recall yesterday, the Greek word, there is an optimal path, and then there is a generally safer path. Yes. So it is all there's some slight difference over here, and then different formulations will give you a different behavior. But they generally have this form, and if you can match this form, you understand what is happening. So what we're trying to do is, yes, update our current U value to a new one. So why do we need this update step? Because when we start out, right, we don't know anything about the world. So the utility value everywhere is 0, right? This equation does not hold. Like this equation is valid when it is at the when we know about the world. Like this equation is valid when we know about the world. But when we start out, it is all 0. So we don't really know. As we explore the world, we can have some rough estimation of U of the utility at some states. Then we can start to perform that calculation, right? We will start to perform that calculation through multiple try and errors and runs inside the world. So now let's move to the deep Q-learning. So from the idea of updating towards a desired value, we have this equation, and you can match the term in the code in the collab notebook to the individual terms. Then for the deep Q-learning, deep Q network, what is different from that? We still have that idea of updating, but it will be formulated in this idea of similar to a neural network. So you have your input. The input will go into the model. The model will give out a certain prediction of utility. So y hat represent an estimation, a prediction. Then we have to compare against a desirable value in order to calculate the loss, the difference, the loss function, like whether we are very close to the value that we want or not. And then we do the back propagation, right? So temporal difference here is maybe this will just complicate problem, right? I will delete this. Expected utility. Yeah, expected utility. Yeah, so there is an expected utility. There's a desired value that we need to calculate in order to compare and contrast against our network prediction in order to get it working. So now there is two things that we both need to learn, right? There are two things that we both need to learn in parallel. One is the weight of the model. So the weight of the model is also random at the start. And because we have not experienced the world, the utility value of our model is also not the best one, right? They are basically random, like 0. We don't really know anything. It is only when the agent start exploring the world, then we can calculate some sort of expected utility. And from that expected utility, we will try to train our model to match that. And how do we get that expected utility? Yes, again, we use that equation, U equals R reward plus the maximum value, right? So this is how we get that. So the question now is, okay, sure, but if we use the comparison to update our model, then what are the starting points for us to even apply this equation, right? Where do we even start to apply this equation to get our expected utility? So that is where we will now go down to the implementation and see how the code does it. But first, I will share with you the bigger visualization of the array that will be present in the program. So when the agent sampled the world, it will start storing the transition, right? It will, so even though I said yesterday, the idea of reinforcement learning is that there is no historical memory. That is not quite, that it is not quite strict in a sense that we cannot remember anything. Definitely, we have our Q function, we have our Q values that we can bring forward. And we also know what is the different transition. So this array here, right? This is one, we can think of it as one unit, one transition unit. So we start at state ST, we take a certain action A, that action A give us a reward, and it will result in us being in a new state ST plus 1. So that is the whole transition. SARS. Yeah, SARS. So that is the one whole transition that we can capture. But this one transition still have that understanding of Markov chain, right? We only know where we are at the current state and maybe at most what is the next state. We don't really know ST minus 1. We don't know at the back what happened at the back. And we also don't know if what is happening in the future. Yeah, basically, we can store this transition in a memory, but all of these transitions are discrete, are treated as independent. So why is the Markov property holds is that we don't have a trajectory. We don't have a list of the number. Let's say I was in node 1, node 2, node 5, node 10. We don't have that sequence. We don't have the sequence of the previous run that we try. We only have one transition, like one transition. And this transition still follows the Markov decision, right? And then how is this transition being stored? So it is being stored as like a very big array. And you can visualize that when we go into the code and there is a term that is called a state, let's say state. Then inside that state is a different data point, like each row is a different data point. So if you do machine learning, right? If you do machine learning, you can think of this as a batch. So in a batch, you have multiple data points being processed at the same time. So what does this visualization mean? So if the state, right, if the state has 4 elements, then the first row will have 4 columns. Yeah, so one red box here just signifies one entry point. Each row is a data point. There's one entry point. I hope you can catch this. So basically, my idea is that when you go in, look into the code, ST might represent a batch of state. AT might represent a batch of action instead of just one single action. And yeah, so when we train, we can push in a big batch of state, a big batch of action, a big batch of reward. But when we try to inference, right? When we try to inference, we probably only put in one input, and then it will spit out 4 action. Similarly, so Q is our Q function, Q table. The rows will signify the data point, and the columns will signify the different possibility. In this case, let's say there are 4 different actions and there are 4 different columns. Okay, let's move to the code because I think now there will be back and forth between the code and the slide, and I think it will be more practical to look at the code straight away. Oh yeah, it completes. Yeah, it already completes the training, and you can see that the score is peaking already. The score reached 500, which is the maximum that we allow in this environment. And the final cell is just running a visualization. So the visualization is refreshing at 0.2 second, I guess. But the idea is, yeah, you can see the pole is like wiggling around, and yeah, it is learning what it is supposed to do. Keep being straight. So let's go all the way up, all the way up. So first, yes, Python pip install, the, what do you call that, exclamation mark tells us to pip install in the terminal instead of in the Python environment. So you need to get the Gymnasium classic control first. So after you install that, we will go to the gym, which is the OpenAI environment, and we have like matplotlib to plot, and then you also have all the function. Okay, here it is quite there is more thing to see, right? Here is like a Python built-in data structure. So this data structure, like name and tuple and dequeue, they help to manage a list of stuff, right? A list of stuff. And then there are also like a torch, which is your neural network. I will not be focusing much on the torch because I think it is out of scope of this workshop. But then I hope if you follow down the path of machine learning and deep reinforcement learning, you will encounter it at some point in time. And I will try to explain as much as I can, but I will focus more on the reinforcement learning component. Yeah, so down here, we're just defining all the display and GPU. Right, so this is turn on GPU, turn on CUDA if there is one. Okay, so now transition, it was named tuple. Maybe I can start on A equals name. Stop this. Yeah. Name tuple. Name tuple. A, B. Okay. So now A. So now if I print A1, oh, take 2 position, 3 is given. Transition. Append transition arguments. Okay. It's 2 positional argument, but 2 is given. AB equals 1. Oh. Okay. Why? First, second is one. First is okay. Sorry. Yeah. So name tuple. So first we will define what is So what does name tuple mean? The first parameter will tell us the, let's say in a sense, the data type, like a class, right? Then the second param will be the subsequent name of the element, right? So let's put this as a bunch, right? A bunch. So then there's a first element, and then there's a second element, right? So now if we try to initialize, let's say A equals A, first element, second element. Right. So it will, wait, 1 second, bunch. Three is given. Oh no, okay. So first, yeah, the second element define how many elements is there? How many elements? Second parameter is how many elements and the corresponding name. Yeah, so you can see that when we try to do A equals first element, second element, then it will be packaged as, you know, an object called bunch, right? It goes into an object called bunch, and then the first element will be what we put in over here. So why do they do it like this? Just to make sure that, yeah, we can see that there is a state, there is next state, there's action and the reward, which is which is precisely this SARS component. So that will be the thing, right? That will be the transition that is being stored as one. So now we will define a replay memory. So this replay memory will be a storage place for the interaction that you did in the environment. So yesterday, if you do your if we run through the program yesterday, then every time it runs through the environment, it will update the utility value and then move on. It doesn't remember anything. So that kind of seems like, you know, the Markov decision is being followed. But here, like I said, we can technically store the transition. So each transition still follow the Markov decision because it only sees ST and ST plus 1, which is in the future, one step in the future. It doesn't know what is in the far future. It doesn't know what is in the far past, right? So the property is still hold. It's just that from this previous experience, we can use them to calculate our utility function, right? So we define this replay memory object. We can push them in, which is, you know, add into this array. You can see that self memory is a DQ. Basically, just think of it as a list, right? DQ, there's a list in the memory. Then every time we have a new transition, we append that, we put it into our memory. Then sometimes we can sample, meaning that random size. Sample is just, you know, pick a random size in the same batch size, and then we can also query how long is this memory, right? Then now is our machine learning model part component. So you can see that there's a DQN, NN modules. If you know PyTorch, then this is how we do that. So NN modules, we have to, the class DQN has to inherit, right? So this is parent-child inheritance, OOP style. Then after that, you can, so this is, inheritance, super init following the parent, right? So after that, we will set up our linear layer. So in deep learning, deep reinforcement learning, the main problem, the main issue is first, your environment. How do you define the environment? It is, you can also use, be creative in the neural network architecture. But I think that is not as prevalent as machine learning. So if you recall machine learning nowadays, there's like a diffusion, there's transformer, etc. You can do so here as well, but it will just complicate things. So, and then because for our current task, we only have four state variable, the angle, the angular velocity, linear and linear velocity. So a few linear layer is enough. So first, yeah, you have to match the size of the observation, which is 4, I believe, or later, yeah. We have to match the size, and then at the end, we have to match the action. And then forward is just a simple forward pass with a ReLU function. Yeah, linear unit, rectify linear unit, yes. So batch size, yeah. So batch size is the number of transition sample from the replay buffer. So this idea of a batch, right? This idea of a batch, which is a bunch of data points, we take them out as a batch. So if we put them as 65, 128, okay, that's a lot. So 128, if we take them out as 128, then this big column will have 128 entries. Yeah, this big array will have 128 rows. So because this is a standard process, a procedure in machine learning, in training the neural network, you train them in batches, you train them with a lot of data so that you can average out instead of having a very big fluctuation. So you have your batch size. So gamma, remember gamma is a discount, then epsilon. So epsilon here is your epsilon exploration, like exploration tendency, I would say tendency. So as you can see here, we progressively decrease that, right? So at the start, we would like to explore a lot. So even though you might have some best action to do, we would still want you to explore a lot because it is at the start of the environment. Then as you improve, we will try to decrease the exploration. This is just the rate of decay. How here is the update rate. I will touch on that later, update rate. And this is the learning rate. Yeah, for the neural network, actually, for the neural network. Okay. So now we have our action and our state. So for the action, we can query directly from environment.actionspace.n. So this is from Jim. Right. If you define your own environment, you can probably just key in the values or in some other form. But not every environment will have this attribute action space.n. Right. Then similarly, we get our number of observation using the len.state. So here we, from the problem definition, we know that it is 4 states. X dot, theta dot. Right. But then they try to do, they do this so that if we change the cut pole problem, right, we change this cut pole into something else, it will still work. So, okay, now there are two network, which is the policy, always active. This policy is used as the agent travel experience the environment, where the target is a slow update. We will see that in action. Yeah, we put in, so they have the same architecture. You can see that DQN, same architecture, same number of observations, same action. They are basically architecturally the same as each other. They just have different roles to play. And .2 device just mean that we will push them to the GPU, yeah. Because in parallel programming, you have to isolate, right? You have to give the values to the GPU before it can be parallelized. Yeah. Then there's also this thing called target load dictionary. So basically, when you initialize, you have random weights. So now here is just saying that, okay, copy and paste the weights. paste the ways. So yeah, policy and target net, they started out being the same, but the way they updates will be very different. Then optimizer and replay memory will be, so optimizer is the standard, yeah, standard ML. You need to do the gradient descent, like for gradient descent and weight updates. And then now here we have our storage, right? Our storage memory. And we want to store around 10,000 10K transition. Remember, it's a transition, not a trajectory. We don't know any sequence. We don't know the correct sequence of action. We just know the individual transition. So the Markov property of no history still hold. Yeah. Okay, that is the setup, I believe. Okay, so now there's a select action, right? Select action, threshold, sample up threshold. So over here, it is just trying to do the epsilon. So you start at like just now 0.9, and then you progressively decrease. You can see that the exponential down here, exponential minus step done. So as the step start to increase, then the exploration rate will also start to decrease. And there is a certain threshold, right? If the threshold, then you start to random, you roll the dice, and then if the dice is larger than the threshold, then you do the best action. So this is exploitation, right? T1 max, return the largest column of each row. Yeah. And then else it will just be sampling. Yeah, you sample, you just take random action. So you can see that T max, so policy net, okay, policy net, you input the state, you get out the action, and then you take the maximum action, which is here. Yes, you take in the action, you take in the state to that policy net, it will get you out 4 different possibility of action, and each of them will have a certain utility values. Then the max will just take the max and do that action, right? Take that value. Yeah, take the max and view 1 So you can use shape and view. You can use print. You use print or the array, right? Array dot shape to inspect. So if you are in the TikTok, I guess TikTok talk yesterday, the guy also emphasized the idea of dimension. Right? You have to, when you deal with machine learning and neural network, you have to constantly use this inspection, like use this to check for the dimension, then match the dimension of different layer of different like layers, input output, things like that. These are the most troublesome part. So here and then here is the just a array to store the episode. Okay, now down here is just the plotting, right? Plotting maybe it's not quite important. So optimized model, you can also follow the link inside here as well to see what is happening. So optimized model, what it does is first it will memory.sample. Okay, so now you see it will start pulling information from that memory. Maybe by this stage, I think I can start showing this diagram, right? From this diagram. Okay, but actually, what does it do actually? So here is how the DQN is trying to do. This is actually from the paper, the original paper that start DQN. It is very different from our COT-POL problem at the moment, but it highlights the same idea. So why does the DQN can be scaled to higher dimension? Because here, so on the left will be your Atari game. So this is the original paper, original research paper. So they deal with Atari games. And then this image will be, let's say, 100 by 100. So it is very high dimension. And they will just do your standardized machine learning techniques, such as convolution. This is the ReLU layer. another round of convolution, fully connected, things like that. And what is at the output? The output will be the Q values. So here will be your state, your S, and at the end, there will be a number. So if there are, in this case, 13, like 13 actions, then it will output 13 columns, right? This diagram. If there is 13 action, it will output like 13 columns. So you, in a sense, you are matching a value, a utility value to an action. And then this is only applicable to discrete action. Yeah, discrete action, because for continuous action, it will be a very different game altogether. And I think we don't have time for this continuous action and stuff. And reinforcement learning is a big topic, and there is a full course dedicated to it. But now I just want you to get familiarized with discrete action, discrete environment, how to do the tabular way, and how to do the neural network way. So yes, so the neural network that we just set up will take in the state and output the various score for different action. And how is it show? It will show like, it will show up like this. So when you put in this image S, it will spit out, okay, that is yeah, it will output. In this case, there are 3 actions, right? You can only control this path up, down, on, not control at all. So the output of the Q value will be 3 values. The output of the Q model will have 3 values. And each of the values we can compare, like we can compare against each other, right? So in this case, okay, 3 options, any options will do. But as it sees that the ball is starting to go past the goal, right? It's starting to go very close to the endpoint, then it will flip the image, not flip the values. So it was saying that, okay, up, actually here you should do up, and the rest will have negative values, because only when you do this, you have like higher reward, higher chance of winning, right? Same for here as well. Continue to go up, and after it bounced the ball away already, then the value stays the same. Like, it doesn't really matter because the ball is not in your corner anymore. So that is how it is being represented in Express, right? So this is a big picture of the loop, of that training loop. So first, we will be going out into the world, explore and try out. And as we explore the environment, we will store the transition in the replay memory, right? We will sample the environment and record the memory update. So we store information in this memory. And then we will, after we collect a pile of transition, we will start to take the memory from that, start to do optimization, right? So we will start to optimize our neural network model, right? And then our policy model will also start to choose action as well, right? So this is a policy net. But then also you will ask, okay, then why is there's a target net then? Because the target net helps to stabilize. It helps to stabilize the calculation. It is reinforcement learning is ultimately a numbers game. You have to simulate, you have to roll out for a very long time. It is a probability, like every action you take, there is a probability of consequences. And it is only when you start going out and play, you will, the agent will learn what is that distribution. Sometimes you will have outliers, and those outliers will make your updates wrong, right? Sometimes some person can be very lucky, buy the lottery and win at the first time, right? And then he said, okay, I buy just a few tickets and then I win already. Lottery seems pretty simple, isn't it? But then that is just an outlier. He has to keep buying and buying and buying to see that, oh crap, actually winning is just an outlier, blip in the big picture of things. Yeah, so therefore, if you keep relying on like every experience to update your belief, that would be very unstable. It is best for you to, let us say, experience for a month, then okay, after a month, then I will start to generalize what is happening. instead of, you know, every day something new happen, then I change. Yeah, so for example, one day, let's say recently there's a flying plane, right? Like flying plane, the door go out the window, then okay, flying plane sounds like it is a very dangerous mode of transportation, which is not correct. You shouldn't update that frequently. You should only update in a larger horizon. So that's why we have this dual policy net. So okay, now let's get back to the code. So this is what is happening. It will reach down to the memory and sample a batch of transition. Okay, here the transition zip transition here. What it is trying to do is converting batch array into a list of array. So you can see that state batch, action batch, reward batch. So they will form the shape like this. Yeah, they will form a shape like this. So there is a row, which are the sample size, and then there are columns, which are the features. And then this is where we start calculate our state action values. So what is our state action values? Our state action values is the policy net that is being outputted by looking at the state. And then we will choose the action that we chose last time. What does that mean? Let's go back here. Right. What that means is that, so when I see a state, let's say state S1, I go through the policy net. Yeah, so this is DQN. And then it gives me 4 possible outcomes. Right. But then we don't choose the highest action. Because you can see that we start this one. We say that, okay, last time when I see state S1, I take action number 2. And then I transition myself to state S2. And the reward I have is this. So now when we put this in, we have to follow what we have done earlier. We have to take action number 2. So 0, 1, 2. We have to take this action instead of taking the maximum. So that is what it is doing. So that is what is being done here. That is what is being done here. Yeah. So I put in my state into the policy. Then I get in like 4 values. But I have to take the action that I did last time. Because I'm trying to replay the memory. You see, I'm replaying the memory that I have stored. Okay. So I have a certain value. I pick this value, I pick this column, so I have a certain value. I have a certain prediction of the utility. But then the question is that utility correct or not? Is it the desired, is that a desired value that we want? So that is why we need this. So what we did just now give us the utility y hat. But then we have to compare that against the expected utility y. And where does this come from? This comes from the target net, you see? So there is an output prediction. So like I said just now, so the state action values, the predicted state action value will follow our memory. Then after we get an output prediction, we will start having a label. So this label will follow that gamma plus reward formulation up here. And this is using the target net. Up here, we're using the policy net. So you can see there are two networks being used. The first one is the policy. So it is not yet updated well. And the later one is the target net, which is slow update. The target net is slow update because it wants to provide a certain stability in the training. Like I said earlier, we don't update our belief that quickly every day, every second, but we should, take a while to reflect, then update. So that is what the target net is doing. But then we will continue to, as we operate inside the world, like every day, right? We will check against our current belief, right? we will check against that. So we still use a very fast update policy net, but for when we want to check against the label, we will use the target net. And what it does over here is non-final mask, is that, so you know that when you are at the final stage, there is no next state. So when you're finished already, when you terminate, that is all. Like you end. There is no future state for you to look. So in this case, right, ST plus 1. So if you are in state, so if let's say G is the goal, if you're in state G minus 1, right, then you take an action, you go to state G, and then you get a very high reward, like 100 plus 100, because you win already, kind of you win. But then if your S is, if your current state is G, there's no future state because you just win, or like the episode just end. So that equation is just trying to eliminate that, eliminate out which is the final state and which is not. And how does it know if it is a final state or not? Yeah, non-final mass, non-final target state. How does it know that it is a final or not final? Then it will use state action reward transition. The non-final mass tensor tuple map is not none. A final state would have been one after the simulation has ended, right? So there is a signal telling it whether it is terminated or not. And if we look back up, I think it should say state action next stage. Yeah, so probably state action next stage. And if next state is N, then it will automatically convert that into a no more new next state, basically. Yeah, I will not go down into this. You just know that it will filter out the correct one. But the main idea is the same. The main idea is the same. We have to calculate a label, right? We have to calculate a label for us to even compare. Because for neural network, we want to have that loss function. We want to have the comparison between our prediction and our expected value, or the label, the ground truth comparison between the prediction and the label, in a sense, the label, in a sense. And from that, we do the optimizer, zero gradient, loss backward, propagate that back, update. So these are standard machine learning techniques. So, and down here is just the rolling out, right? So run training process. Keep running the thing. Keep running the thing, right? So for how many episodes, like if we are doing like CUDA, then we are taking 500 episodes. And down here is where the gym environment formulation is done, you see. So there's state information. So information we don't really use. So after it reset, it will give us back a starting state. Then we have to convert that into a tensor because we're using PyTorch, and PyTorch needs a certain data type, which is the tensor torch tensor. We have to convert that into tensor, load that into our GPU. Unsqueeze just mean okay, unsqueeze. So you see down here, right? Because we define our neural network as being able to take in a batch of values. So for example, if our columns is 4, if we have 4 columns, normally in a batch we will have, let's say 10 rows, 10 rows, 4 columns. But now we only have, you know, 1 data point, so we have 4 columns. But we have to explicitly tell it to say that I have 1 row, right? Even though we don't have to explicitly say I have 1 row, you can just say I have 4 columns. But we have to explicitly say that. Yes, that is the idea of the unsqueeze. You can read up on that, how the unsqueeze work. But the idea is to explicitly tell the machine learning model is that I have a batch, and that batch number is 1. So after that, the action, there will be an action, and this selection action is from the state, right? This select action we have defined up there. If it is at the start of the environment run, then it will explore a lot, run a lot of random movement. But as it goes, then it will start converging and converging. So then you will put this action into the environment.step. So stepping here is, it is stepping one time inside the environment. And then the environment will give us back the observation reward and whether it is terminated or truncated. So terminated means it has reached the final goal. Truncated means, okay, like the timeout duration has elapsed. Yeah, so these are the signal for us to know whether an episode has finished or not. And these are the observation and reward. So technically observation and state are the same, but I don't know why they mix up the terminology to make us more confused. But the idea is the same, reward. Yeah, you load that into the tensor similarly. And then next stage will be the current observation. So yeah, next stage. And here is where you put that chain, right? State, action, next state, reward. Oh, reconnect. Yeah, state, action, next state, reward. So this is the transition, like one transition at a time. And you push it up. Then you, go to the next time step, next state equals next state. Then you run the whole optimization model that we have set so far. Okay, so down here is where we start to update our target model to the policy. So sure, we are training our model, but the thing that we train is the thing that we explicitly train is the policy net. So when we do gradient descent, right, we are gradient descending on the policy net actually. So then how does the target net knows if it should catch up or not, right? Because so let's say you are, So the policy net after 100 tries in the world, it have a rough sense of what is the best action to take. But then it has to communicate that to the target net. It has to update the target net. But this update is not a gradient descent. It's just a simple linear interpolation like this as well. So you see, back to that idea of linear interpolation. You have x1 is where you are at the moment. You have x2 is where you want to be. And then you have a certain learning rate percentage. Then that will give you x3. So similarly, you can match. So tau here is the percentage. So I'm starting at the target net. So this is where I am at the moment. Then I want to go one step closer to the policy net. But I don't want to go too aggressively. I just want to go a percentage of it. Yeah, so if you see that tau and minus 1 tau is this one, yeah. So it's a different version. Just now we are using this upper version. If you recall, the upper version is a new update is our current update plus the learning rate of the error, right? That is the top part. But down here in the policy, it has a different form, but ultimately mathematically the same. So tau x2 and 1 minus tau x1, which is matching this. So basically it is trying to copy and paste the weight. It will try to copy and paste the weight over to the target net, but it doesn't just blindly copy and paste. It will go somewhere in the middle, right? Linear interpolated. Yeah, so why are there these two nets? Again, the policy will explicitly take action. The policy will take the action, while the target net provide a more stable update. And it is the ground for us to use the Bellman equation. Yeah, recall, to get the Bellman equation label, we have to use the target net. Learning. Yeah, I think that is all. And after that, it's just, see how it goes. So you can see, like, how do we interpret this graph? So at the start, it will explore a lot. So the duration is very small. The orange one is trying to smooth, right? It's trying to take the average. So at the start, we are like exploring. There's not much to really do. But then after a while, as we decrease the exploration, it will tend towards a kind of a good behavior, right? It will tend towards a good behavior. And from there, it will start keep exploiting, and all the way up here, it has exploited enough so that it reached a maximum goal. So this is how you like interpret the whole thing. So down here at the bottom is just testing and visualization. Yeah, take the best action. So now we only take the best action because we are inferencing. We are no longer training. We're just inference. So basically just return the policy and take the maximum. Input the state, pass through the policy, take the maximum. And down here, maybe I want to test, maybe one episode is enough, I think. One episode is enough. Then down here is just plotting, like plotting out the game. Pause a bit so the plot are updated. Yeah, so this structure is the same as the training structure because we still need to evolve inside the environment. It's just that now we have to render out. And when we render out, it will look something like this. Right? It will wiggle, jiggle, a bit. Yeah, you see like boom, 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 boom. So this is, it has learned, it has already learned. So you can see that the way we address the weight, right, is this TargetNet state dictionary. Yeah, state dictionary. And if you want to save that out, you can do PyTorch. Save and load model. Load model. Yeah, so down here you can see that state dict. Yeah, state dictionary is the values of the model. Then you can save them out into a file and load them in. So yeah, after you have finished your training, you can save it out to a file. Then when you are ready to present to the judges or yeah, demonstrate, then you can just load it in. You don't need to run another training again. Yeah, so that is this idea of the state dictionary. Yeah, so that is all for the coding part. Now I will share more about the building environment. So usually people will use the Gymnasium, OpenAI Gymnasium as a benchmark because they have already figured out all the environment, which is quite good. And the way they do it is, yeah, so there's an action space, there's an observation space. And then the two main important thing is that, yeah, I need to reset the environment. I need to step in the environment, basically that, yeah, two steps. I can reset. How does my environment evolve as the agent take action? So those are the two important components. And then in the reset, then you have to give us the initial state. And at every step, you will give us, you will give the agent the state, the reward, and whether the environment is terminated or not, right? And inside here is up to you. Like you can define the state, you can define whatever you want. The environment is all your decision to make. Because yeah, again, we are not landing an aircraft, right? We are not landing aircraft anymore. We're trying to tackle a real world problem. Yeah, we're not doing this. But we can follow the outline of how they write the environment to make it easier for us, right? To understand and visualize. So that is for the building the environment, gym, right? And I think that is mainly that is it. I think tomorrow is already the submission point. So I wish you all the best. At the moment, so you can see that the reinforcement learning, I have introduced the grid world, the deep Q learning, but then they are all operating on a discrete action environment, right? Like even though just now the cut pole, it is just either go left or go right. It doesn't go left by 0.5 centimeter or by 0.8. So that is in the domain of continuous action. And in continuous action, definitely we cannot do this, right? Because the way we define our Q function over here requires like 13 different output. So for a continuous action, how do we do that? So therefore, we have to utilize the idea of a policy network. So if you recall, yesterday there is a value iteration, which is what we have done, what we have been doing for the DQN. But then there's also the idea of a policy network. So for the policy network, we will take in a state, and then that policy network will output an action. And then there is a, how do I put this? For utility function, right? It will take in a state, it outputs a value. For policy network, it takes in a state and output an action. And how do they play out together is in this manner. So you have a policy and then you have a value. So as the policy play around in the environment, the value will critique like whether your policy is good or not, right? It will give the value. And how do we update these? Is by, so there is a formulation to update that. You can see that in the policy neural network updating step, there is a value function. There's a component. So in a sense, in order to make a better policy, it has to reference, it has to query from the value function. And the rest is similar to machine learning. You just gradient descent and trigger the optimization loop. So but then this is for your information, and know that there are extension to this idea of reinforcement learning. Yes, that is all. I hope you have learned a lot and have a primer in reinforcement learning. I think it is quite early. We are 30 minutes early, but since tomorrow is already the deadline, I also don't want to hold you back, and I wish you all the best. If you have any question, you can raise them now. Yeah. Yes? No? No? Okay. Then thank you very much. I will still be here if you want, if you need.